magnetic field lines for the conductor carrying the current. Now, suppose we are having a current carrier and which is a straight conducting wire, then by the right hand thumb rule, if the thumb gives the direction of the current flowing in the conductor, then the magnetic lines, field lines, they are in the direction of curvature of the fingers, and so this is the, and the curvature of finger will be like this. So the magnetic lines force will be in anti-clockwise direction. Whose center is the current carrier. Now, instead of a straight conductor, if we are having a coil, and this coil current is passing through this, the same method we will apply. Here the difference will be in the right rule. If the fingers shows the direction of current, then thumb will give the direction of magnetic field. Here the thumb is showing the direction of the current, and fingers, curvature of the finger gives the direction of magnetic field. Here it is a reverse of this. If the finger shows the direction of magnet of current, then thumb will indicate. So here the direction of curvature is, current is in the anti-clockwise. So magnetic field will be perpendicular to it, so it will be this one. So if we look at it, if this is the coil, the current is passing anti-clockwise, then this will behave like a N pole. You can have the arrow, and arrow are anti-clockwise, so it is N pole. If the current passes into clockwise, then this will be a S pole. The direction of S you can give like this. So the as here, what will be here? The upper pole, this will be a north pole, because it is in the anti-clockwise, and the base of this is south pole. So the current carrying coil will behave like a magnet. If we see from upper side, then if the current is passing in the anti-clockwise, it will behave like a N pole, and if it is the current passing is in clockwise, then it will behave like a. So if it is the current coil, the current passing through it is the anti-clockwise, then we will show the magnetic field lines in three-dimensional. It is in one dimension, two-dimensional. It is in the three-dimensional, and at this point the current is coming outside. Here current is going downward, so we will put it circle and dot. Dot means coming outward and perpendicular to the board. Here the current is going downward and it is perpendicular to the board inside it. So we will write it cross. Here we will write the dot. The magnetic lines for this cell will be in the anti-clockwise. Here it will be clockwise. And as we go near to the center, they are a straight line. So these lines will be like this. So in the center, almost all the lines. So magnetic field will be decreasing or very less outside it, and this side is also less, inside is, but magnetic field will be maximum in this side, and it is maximum at the center. This is the case if the one coil is there. Now we are having two coils, one by one. This is one coil, and this is the current is coming outside and current downward. This is current is going outside. So if we connect it, we can have like this. Then current is passing like this here. So here it is coming outward, so it will be anti-clockwise. So anti-circle, anti-clockwise, anti-circle. The second coil is here, it is also outside, it is anti-clockwise. So here, if we say in between them, this is anti-clockwise, so they will cancel it. So the magnetic lines of force will cancel each another which are nearby it. Whereas in the center, the magnetic lines will be supporting and they will be all in the same direction. Here also, when it is crossed, then the magnetic lines of force will be clockwise. This will be clockwise. Here it will be clockwise. So, and here, this is going upward and this is going to be. So they will cancel. Here, this will be clockwise. Clockwise. So here the direction for this field line is opposite to this. So they will also cancel. So the field lines which are at these ends, they will be cancel each other. So magnetic field will be minimum here, maximum field will be maximum here, maximum means it will be minimum here. So if we have instead of 2 turns, if we have a large number of turns, this is the 1 turn, this is second turn, third turn, fourth turn and so on, then the resultant magnetic field, here they will be cancelled and the magnetic field will be maximum here, magnetic field will be nearly zero outside the coils. So we can explain easily the magnetic field. If there are the coils and the turns are nearby each another, they are closely near, then the magnetic field will be maximum inside it and magnetic field is almost zero outside it. So this principle is used for the solenoid. Now what is the solenoid? Solenoid, if we are having a solenoid, now what is the solenoid? If we have a copper conducting wire, very long wire, and we make it enamel. Enamel means if it is conducting inside and outer side is non-conducting. So enamel copper wire is used and it is wounded on a circular rod. So its shape will be a spiral shape, just like the spring, it is like a spiral shape. So these are the one end, another, this is the outgoing and current is passing through it. So we are having a large number of turns which are close to each another. They are in contact with each other. The winding is very close, but since it is insulated, so the current will be same in all the turns, but it will not conduct in the forward direction, it will be in the circular direction. So the length of the solenoid is very large than the radius of the solenoid. The number of turns are very close to each other, and if we say N is number of turns per unit length, N should be constant, means the winding should be equally and the number of turns per unit length should be equal and they are equally spaced with each other. Now, if we have this N and we pass the current, if we pass the current here, then it will be the magnetic field, we can show magnetic field lines with either this is the turn which is coming outside, this is turn which is going outside. So these different turns are given. These are, the current is going upward and it is going downward, upward and downward, upward and downward. So here, as I told earlier, the magnetic field here will be equal to, nearly equal to 0. Here the magnetic field nearly equal to 0. Magnetic field will be maximum inside it or in the, on the axis of the solenoid. Now we have to find the, what is the magnetic field for the solenoid. So to find the magnetic field, what we will do? We will have a imperial loop, and we take a imperial loop A, B, C, D. This is an imperial loop. This is the, suppose the direction of the imperial loop is like this. Then we have to find the magnetic field using Ampere's circulator law. So by Ampere's circulator law, B dot dl is equal to mu 0 into summation of I. Now here our Ampere loop is ABCD. So total, here we can write, this is for A, B, C, D, A. This is the closed loop. So we will divide it all 4 parts. So this will be equal to integral A to B dot dl, B to C, B dot dl, C to D, B dot dl, plus D to A, B dot dl is equal to mu 0. Now if the length of AB is small n, then the number of turns will be equal to n into L. This will be the total number of turns in the length AB. So current will be equal to n into L into I. This will be the total current. N is the number of turns per unit length. L multiplied it. So N into L will be total number of turns in AB length. So it will be 0. Then the summation of I will be equal to, is equal to N into L into I. So put it here. Now for AB, it is well inside it. The magnetic field, if we take A to B, the magnetic field is suppose in this direction, then magnetic field R and DL will be in the same direction. So here angle between B and DL is 0. So here AB, BDL, here vectors is there, BDL cos 0 plus BC. BC, if we take any one, then BC will be perpendicular to the B. So theta is equal to 90. So here BDL cos 90 plus CD. For CD, B is equal to 0 into DL cos 0 plus DA. Then BDL cos 90. Now we know the cos 90 is equal to 0. This is multiplied by 0 is equal to 0. Here cos 90 is 0. So this term will be 0. So the only term for the magnetic field will be this term, and that will be equal to line integral AB BDL is equal to mu 0 N into L into I. Now the magnetic field is constant inside it, so we can take it outside. B, since B is constant, so B line integral dl will be equal to mu 0 n into L into I, and the line integral of BL dl will be equal to the length AB, which is equal to L. So here B into small l will be equal to mu 0 n I L. So this L will cancel. So B will be equal to mu 0 n I. So here we say the magnetic field on the axis of the solenoid will be equal to mu 0 n into I. The direction of magnetic field will be given by right hand thumb rule. Here the current is passing through it. If the current is this side, then magnetic field, if the current is moving, then magnetic field will be in this side. So here the magnetic field will be in this direction. So here instead of this we can write 180. It makes no difference. That is also equal to 1. So minus 1. So the result will be same. So the magnetic field B will be and its direction will be on the axis. Now the magnetic field will depend upon B does not depend on length and the radius. It doesn't depend upon. B depends on n number of turns per unit length and current passing through it. So the magnetic field for this solenoid, it will not depend upon the length of the solenoid. This is the total length of the solenoid. It doesn't depend. The radius of the solenoid, it doesn't depend upon the length of the solenoid. It doesn't depend upon the radius of the solenoid. It will only depend upon number of turns per unit length. That is equal to small l and current passing through it. So if we draw the curve B with N, it will be a straight line. If we draw the curve B with I, this will also a straight line curve. So the magnetic field will be equal to, here you have to write a mu or mu 0. You can write mu 0. Here is the mu 0. Now if instead of air the medium is other medium, then what will be the magnetic field? If mu is permeability of medium, then B will be equal to mu into N into I, or this is equal to mu 0 into mu R N into I. This will be the magnetic field when the permeability is mu, means here the medium is not air, here the medium is a particular medium, then the magnetic field will be equal to mu times Ni, and or we can write mu 0 mu R into Ni, where mu R is relative permeability. Mu 0 is the permeability of the space, free space or air or vacuum, and mu is the permeability of the medium. Now if we have a length of solenoid is small, in this case the length of solenoid is very large. Here if it is very small, suppose this solenoid is of this length only. Then it is the center of the solenoid. Then, and this is the axis. We make the angle. This angle is theta 1, and this end make angle theta 2. Theta 1 is this angle, which this end makes with this here, with this direction, and here theta is the angle which made by this end with the axis. So in this case, the magnetic field B will be equal to mu 0 1 by 2 mu 0 Ni cos of theta 1 minus cos of theta 2. This will be the magnetic field if theta is the angle subtended by this end with this axis from this side, and theta 2 is the angle subtended by this end with the same direction. Then this will be the magnetic field. If we want to find the magnetic field, we add any end. Suppose we want to be at this end. This is B at center. Now if we want to find the B at this end, this point is. So this angle theta 1 will be equal to 90, and theta 2 and this is extended to infinity. Then this will be 180. So magnetic field B will be equal to 1/2 mu 0 Ni cos 90 minus cos 180. Cos 90 is 0. This is minus 1. So B will be equal to 1/2 mu 0 Ni. So we can say the magnetic field at this end or at this end or this end, it is just half of the magnetic field at the center. Now, if length is infinite, then theta 1 will be equal to 0 and theta 2 will be equal to 180. So this will be equal to 1 and this is equal to minus 1 plus 1. So result will be same. B will be equal to mu 0 Ni 1 minus 1, that is equal to 1/2 is there. So it is equal to mu 0 N into. Now next is case, if we have iron as a core, means here we have a iron rod. Here is the iron rod. Now we know that the iron is a ferromagnetic substance, so the magnetic field will be very large, and in this case this solenoid will behave like a magnet. It will be N and S. So when we have a core is iron, then this solenoid will behave like a magnet, and we can say that the magnetic field will be very light because the permeability of iron is very large, so it will work as an electromagnet. Because if we pass the current, then it will work as a magnet. If we stop the current, then it will not behave like a magnet. So when we have a iron core inside the solenoid, in that case we will have a magnet. The solenoid will behave like a magnet, and it is a electromagnet, because if we pass the current, it will be magnet. If we remove the current or if we stop the current, then it will be non-magnetic. So we can say, if the iron core is filled inside the core of the solenoid, then this will work as a electromagnet.